Hello. So in this lesson, we're looking at electric potential energy and voltage, and the focus is definitely supposed to kind of be on the voltage end of things. But to be able to understand that, we need to get our heads wrapped a little bit around what electric potential energy means. And to really understand that, we're going to have to first just kind of do a quick little review of gravitational potential energy. Because one of the most important things that I try to get people to understand is that when we're talking about electric potential energy and some of the ideas that we're going to get to in just a moment, if you first ask yourself what would happen in a situation involving gravitational potential energy, you'll probably be saying the right things. So, starting here, I want you to imagine that I've got a red ball and right now I'm holding it really high above the ground. So it's really high up in the air. And to calculate its classic gravitational potential energy, I could use the formula EP equals mgh, stick in the numbers and find out, hey, this is how much gravitational potential energy it has in joules. Now, because it's really high up, we expect that's going to be, at least for this situation, a lot of gravitational potential energy. So, a way that we'll often say this is that being, at least for the way that we're going to be talking about in this lesson, being up here at this point where it has lots of gravitational potential energy means that I can say it is in a region where it has high potential. I would just say that. A region of high potential just means we're someplace where whatever kind of potential we're talking about, it has lots of it. Now, if I just let go of the ball when it's really high up here, all on its own, it's going to fall towards the ground. I don't have to do anything for that to happen. In fact, I'm not holding it up anymore. I'm just letting go of it, and all on its own, it will move downwards. We know from classic like physics 20 and even science 10 stuff, it is losing gravitational potential energy while gaining kinetic. So as it falls, it's going to be falling faster, faster, faster with more and more kinetic energy until when it reaches the ground, we know that at that point, if I calculate its gravitational potential, it'll be zero. Its kinetic energy will be the highest, and it'll actually be moving the fastest it's ever going to be moving when it reaches the ground. So, if I kind of go with that way of talking about what was happening way up at the top there, I could say that when it's at the ground, it's in a region of low potential energy. In fact, when it's on the ground, it's the very lowest of low, it's no potential. But it's this idea of being where the potential is high and where it's low that we're going to be playing with in a few moments. So, what if I decide I want to pick this ball up and take it back up there? Well, to do that, I would have to do work. And if I wanted to measure how much work I'd be doing, I need to keep in mind three things. I'd need to know the mass of the object, because if I did something like I doubled the mass of the object, it would take double the work to lift it up to here. I would also be giving it double the potential energy. It depends on the gravitational field strength, and I'm going to assume that as long as nothing too crazy is happening here, we're doing this on the planet Earth, and the gravitational field strength is just staying constant. And it also depends on the height. It depends on how far I'm lifting it to get it back up here. Okay? But if I did change any of those, if I lifted it higher or I doubled its mass or something like that, I can change how much work I need to do to change where that mass is. Now, I want you to imagine what this looks like if we change out a ball, a mass, within the Earth's gravitational field with a charge between two parallel plates. So click back here for a second. See, it's basically the same diagram. I've got a positive plate up at the top here. I've got a negative plate at the bottom, which means there is a region of an electric field between these two plates. And I still get to say the same sort of things though, because I've put my positive charge next to the positive plate. It does not want to be there. In fact, right now, this charge would be feeling an enormous amount of electrostatic force trying to shove it down here, and it definitely wants to get down here to where this negative plate is. So, when the charge is up here at the top, we would say that it's in a region of high potential because it doesn't want to be there on its own. An outside force or something would have to be acting on it to hold it there, just like back here when I was holding the ball up at that high position. So if we do release the charge, naturally on its own, it will move downwards. And as it's doing that, it's losing potential, gaining kinetic, moving faster, faster, faster. And if I want to, take that charge and lift it back up to the top up here, again, I have to consider how much work I would be doing to do that, and that it would depend on things like what's the charge on the object. If I double the charge, it will take double the work. The electric field strength, and unlike the gravitational field of the Earth, I am totally ready to change the electric field that I'm in. I could do things like put more charge on those plates or bring them closer together, and either of those, or both combined, would increase the electric field. But I can definitely adjust that electric field if I want to. And I do have to consider how far we moved it. So you'll notice this is very much like mass, gravity, and height. It's the same sort of analogy, right? And in this situation, if you're being asked a question about what would happen to a charge between some parallel plates, you should always try to fall back onto that idea of what would a ball do if it was released in a similar situation where there is a gravitational field that it's acting in. And if you approach it the same sort of way, taking into account, of course, that we are dealing with charges here and probably parallel plates with charges on them, all of that stuff's great, that you can answer it the same sort of way and come up with a meaningful answer. Now, this is where we start getting into this idea of voltage, because at some point historically, somebody said, wouldn't it be interesting to kind of think of this in terms of the effort it takes, the work that's done to move this up to a higher position for each amount of charge? Now, let me just kind of tell you what I mean there. I'd already said to you that if I doubled the charge, it would take double the work to get it up here, and it would give it double the electrical potential energy. But what somebody said is, but if we're doing double the charge for double the energy, the doubling kind of cancels out. Isn't there a way we could express that? And that's where the idea of voltage came from. Now, voltage goes by a bunch of names. And I'm really sorry about this because it's basically us inheriting not only decades, but centuries of people talking about this concept. So we can call it voltage. We can also call it electric potential difference, not to be confused with electric potential energy. That's what we were just kind of talking about. But electric potential difference means voltage. Or you can get rid of the word difference and just say electric potential. Or you can get rid of the word electric and just say potential difference. And all of these mean the same thing. Voltage is electric potential difference. It is electric potential. It is potential difference. And whether it's on my worksheets, my exams, the diploma, there's a tendency to flip back and forth and use all of these terms when all we're really doing is talking about voltage, a measurement of how much electric potential energy a charged object has per unit charge. So this is our formula. Up here is the electric potential energy. This is where the energy part comes in. Charge down here, this is the charge that we're probably moving in an electric field of some sort. And if I take the energy divided by the charge, I get a measurement of the voltage. So I'm going to jump back to this other slide for just a second, just to kind of try to emphasize what we're talking about here. So if I have a single positive charge and I let it move through this field on its own, and then I pick up the charge and I move it back up to where it started from, I'd have to do some work to do that. How much energy, how much potential energy did I put back into it for that charge? I could go ahead and I could calculate it. Now, I've also said that if we double this charge and we let it go down and then I have to lift it back up again, we would have to do double the work, but we would also get double the energy. Looking at this formula, getting double the energy for double the charge, the double over double, the 2 over 2 would cancel, the voltage comes out as the same number. Voltage is meant to be a measurement of the difference between two different ends in that electric field and how much potential something has moving through that field. This sounds weird, right? It is kind of a weird concept that way. But we do get to use voltage quite a bit because it's a nice way to be able to talk about regions between like parallel plates and how much kind of oomph there is behind what we're doing to move charges per unit charge through that field. That's kind of the advantage there. So if I have, for example, a 3.4 Coulomb charge that I observed to gain 2.6 times 10 to the 3 joules as it moves on its own through an electric field, I might ask you to determine how much electric potential difference there is in that region, and also to tell me if this gain in energy, that 2.6 times 10 to the 3 joules, is an increase in the potential or kinetic energy of the charge. So, just finding out the electric potential difference, it's asking me for voltage. Electric potential difference is not electric potential energy, which is the energy that we're dealing with here, or at least the change in energy, as it might be changing from potential to kinetic or kinetic to potential. So I was already told that it gained this much energy. So that's what I'm going to stick in here as my gain. And the 3.4 coulombs is my charge. So I stick in the values, and I go ahead and I calculate the voltage, and it's 7.6 times 10 to the 2 volts. Now what that tells me is that even if I came along with a different charge that would gain a different amount of energy moving through this electric field on its own, I could still use this formula to do things like figure out that energy based on this voltage. Because as long as I keep everything about those plates probably that I'm using to make the field here, as long as I keep those the same, then I'm going to have the same voltage all the time. Now, the question still was, is this a gain in energy that is either potential or kinetic? Notice in the question it does say that it moves on its own through the electric field. If it's moving on its own through the electric field, that means it's not me trying to shove it around. Objects moving on their own will always move from a region of high potential to low potential. Because remember, that's like dropping a ball, right? It moves on its own. So this must mean that it's losing its potential, which means the gain that it's referring to is a gain in the kinetic energy. Now, there is a whole bunch more that we can do with voltage, and there's going to be other stuff that we do as we get into later sections. But for now, we're going to kind of leave this formula with this idea as it is. And I'm going to tell you quickly, briefly, about something called electron volts. Now, I'm not trying to confuse things here. What I'm actually asking you to do is kind of think of this now as its own separate thing. This is just something off to the side for a moment, because this is actually an idea that we're going to find is a lot more useful when we get into some of the much later chapters, like especially, surprisingly, quantum mechanics. But it's a good idea to at least introduce it now, because if you look at the formula that I've got written there for you, it is the voltage formula that I just showed you. Oh, and I should have pointed this out before. The E doesn't have a vector arrow. That's how I know it's energy, not electric field. But this is the formula solved for energy now. So basically, people that were tinkering around with things like individual electrons zipping around noticed that if we're measuring their energies in joules, the answers come out really, really small. So they wanted a way that was a bit more convenient about them. The solution they came up with is this idea of something called electron volts. And I know the name really doesn't sound like it, but electron volts is a way of measuring super tiny amounts of energy. So where we usually measure energy in joules, here we're measuring it in electron volts. And that comes from the formula because here, if especially we're kind of thinking like the earliest days of people figuring out structure of the atom and stuff, everybody was at least at first talking about electrons. I would be talking about electrons moving through voltages, electron volts. That's where the name came from. Now, officially, this is not part of the metric system. And in fact, with any of the formulas, other than this one right here, where I'm going to show you how to do the calculation, with any other formula, I have to first convert electron volts into joules because everything else on the data sheet that deals with energy deals with joules. But here I can do this special idea. I can basically say that 1 electron volt of energy is what would happen if 1 electron passed through 1 volt of potential difference. Now, usually, and this is where I'm trying to show you what would happen if I put in the right values, if I start to make it so it is like an actual metric unit, I wouldn't write down 1 electron. I would put in that 1 electron is 1.60 times 10 to the negative 19 coulombs, the elementary charge from our data sheet. Going through 1 volt. Oh, this charge going through 1 volt would gain or lose, whether we're talking about potential or kinetic, whatever, 1.60 times 10 to the negative 19 joules of energy. That's equivalent to 1 electron volt. If you look up on your data sheet, you'll actually see that this is written on the constants for you. It's shown as something that you're supposed to be aware of in order to be able to use it for doing conversions. So, thinking back to the example that we did just previously, for example, number 1, where we had figured out the voltage, I say to you, I want to know how many electron volts of energy are needed to be able to move an alpha particle, which is also on the top right of your data sheet, where it shows all the protons, electrons stuff, a charge of positive 2 elementary charges through that same voltage. If I was trying to take that alpha particle and move it from the negative to the positive plate, that would be me doing work. I would be adding potential energy to it because I'm moving it from where it likes to be against the negative plate to where it doesn't want to be against the positive plate. But if I want to do this, I can do it really quickly with this formula, solve for energy in electron volts, because look at how easy it is to write in the numbers. Instead of putting in the charge as a real charge, I just put in its 2 elementary charges, moving through that voltage of 7.6 times 10 to the 2 volts. 2 elementary charges, moving through that much voltage, it's just 2 times that number. It's really quick and easy to do. I get an answer of 1.5 times 10 to the 3 electron volts. This is why physicists liked using it. It let them do the calculations really fast, and it gave them numbers, answers that, well, they look just kind of like normal numbers. Now remember, this is a measurement of energy. This is how much energy, how much work I would have to do on that alpha particle to lift it up to that other point where it's now against the positive plate, and that would represent the electric potential energy that I've given to the alpha particle. Still, this is not a safe number to use in most of the formulas. So I would have to be ready to convert it into joules if I was going to do anything else with it. So that's why I would set up one of my quick little conversions with ratios. I'm putting in how many electron volts I've got. The part that's in brackets here is me making a ratio from what's written on the data sheet, that 1.60 times 10 to the negative 19 joules is equivalent to 1 electron volt. EV on the top, EV on the bottom cancel, and I'm going to be left with my answer in joules, 2.4 times 10 to the negative 16 joules, which I could then use if I want to do something like figure out if I release this particle and that all changed into kinetic energy, how fast is the alpha particle moving? Because the mass of the alpha particle is on the data sheet. This would become the kinetic energy of the alpha particle, and then I could figure out its velocity. But more about that actually in the next lesson. So for now, I'd suggest you take a look at some questions, try them out, and see how things work for you. Good luck with that.